So we've looked at an example of solving a second order linear homogeneous differential equation using a power series solution, and we did so about an ordinary point. And we did it very slowly and went through the steps and clearly delineated each step. Here we're just going to go much faster to get a broader perspective of these solutions. So let's start with this differential equation here. This has singular points, okay, where this is 0, because of course we would have to put this in standard form, and so you'd get a denominator of x squared plus 1 here and here, and hence these p of x and q of x will not be analytic at those points, where a2 is 0 and a2 is 0 at x is equal to plus or minus I, okay? So we have that. So these are singular points. We're going to expand about the ordinary point 0. And the distance between 0 and I or plus I is 1. So the minimum radius of convergence we're going to get is r is equal to 1 if we do an expansion about the ordinary point 0. Okay, so that's where that's coming from. So let y be this. This is the assumed form. And we're going to work on the left-hand side there. So the second derivative is going to be this. The x times the first derivative is here. And we get this minus y here. Okay, so this corresponds to this. This corresponds to that, and x squared plus 1 corresponds to that times this, okay? And so continuing, we'll distribute this power series along x squared plus 1. So this is coming from that times 1 term of multiplying the power series times 1. And this here, well, we have n minus 2 times x squared, so that's where you're going to get a plus 2 from this x squared. And so we get this. And now what do we need? Well, we need all of these to have the same power to combine them. And this will cause us to, so for example here, this starts at 2. This starts at 0, so we're going to take out 2 terms from here. Okay? We're going to take out, so that's 2c2x0, 1 term from there. And then the next term we'll take out will be for n is equal to 3, and that's going to give us this term, because 3 times 2 is 6, and so that's that term. So those are the first 2 terms. We just pulled them out of this. Well, what about this guy? Well, this starts at x is equal to, this starts at n equals 1, so power x. Okay, we're going to pull out 1 term from that, the first one, so it's going to be c1x. Okay, and there's that. And what about this one? Well, we're going to pull out 2 terms, the first one being c0 x to the power 0, which is here, and then the next one being c1x, okay? And now all of these start at x squared. That's what we were doing there. We want them to start at the same place in the sum, so we're going to shift the sum, and we're going to use the same index k. And so doing that here, which we've done many times, we get this term. We get this at the end of the day for the left-hand side of the differential equation. Now, differential equation is 2 sides. The right-hand side is just 0. And so by the identity property, this will be 0. Why is this 0 and not C2 and C0 independently? So how do we get that? Well, this is the coefficient of the x to the power 0 term, okay? This is the coefficient of x to the power 1 term, so that's why that's 0. And this is the coefficient of x to the power k. And that's why we're getting this relation here, okay? So be careful. The identity property is not telling you that the CKs are 0. It's telling you that the coefficients in this expansion are 0. And so these are the coefficients of the powers of x. So we have these three relations. This one here gives us this C3. This gives us that, and we get a recurrence relation. Okay, the sum. Why does k equal 2 here? Well, this is where the sum begins. And we go down the line as we've done in detail with previous examples to get C4, C5, C6. But notice something happening here. Okay, so we just assumed that we have C naught. And this is a second order linear homogeneous differential equation. So we expect, that we're going to have a C1 somewhere. But we look and, well, there isn't any C1 over here. These are just 0 and the rest depend on C naught. So what happened to C1? Well, it's still here. It's in our assumed form. We assumed this form here, so C1 shows up. And if we plug the first few results into our assumed form and factor out C naught, we get this. And we only get one term for C1. So it's there all along, and we just leave that alone. It's okay if it didn't show up in the recurrence relation. And so there goes our two linearly independent solutions. This one here, okay, which we could actually write in closed form this way after considering the first two terms. And we get a radius of convergence here of x is less than 1 by that theorem. And y2, the second linearly independent function that forms the fundamental set, is just x. Okay? And that's totally fine. So let's do another quick example, and this time we're going to get a 3-term recurrence relation. So we got the differential equation. We're going to assume this form. We're going to plug in. We're going to take the derivatives, plug them into the left-hand side, set that equal to the right-hand side, just as we've done previous times. And we're going to get these two relations for the coefficients. Okay, I omitted all those details because now we're focusing on something else. Notice now this recurrence relation is 3 terms, okay? Now, we could do this just as we've always done. So we'll take the K1 term. This gives us that C3 depends on C1 and C naught. C4 depends on C9 and C1. C5, and on and on. Okay, and we just assume we have C naught and C1. Then we could take a look at the assumed form and plug them in, and then combine the terms of C naught and C1 and get our two linearly independent solutions. And this works, but it's you're carrying a lot of terms, okay? Like here, I just over here I just even got lazy and didn't even add those terms. You don't want to keep doing these, right? There's just a faster way. And the faster way is that we know that we're going to end up getting terms proportional to C naught and terms proportional to C1. So why don't we turn off all of the terms that are proportional to C1 while we compute the terms proportional to C naught? And why don't we turn off all the terms proportional to C naught when we compute the terms proportional to C1? That just makes things faster. Nothing wrong with this, but we can make things faster by doing what I just said. And so we'll do that, right? So let's just first turn off all the C1 terms. So just we're pretending that C1 is equal to 0 and C naught isn't. And we just do this procedure while, we'll go through the case. And if we run into one of the terms that depend on C1, then we just set it C1 equal to 0, and we just keep going. So we'll start with here K equals 1. This is going to give us C3. Okay, and C2 here, this is coming from this. Okay, and so we're here assuming C0 is not equal to 0 for this. So C3, the first one, we get C1 plus C0. Well, what is C1? We're assuming it's 0. We're just paying attention on C0. We get that coefficient. C4, again, we assume C1 is 0. And we just continue doing this, okay? And we're getting now all the terms proportional to C0. We do the opposite, right? We now assume C0 is 0 and C1 is not equal to 0. And here now C2 would be equal to 0, C3 would be equal to this, and we now get all the terms proportional to C1. And so assuming this form, which is what we implicitly did to do this, okay, for Y1, okay, where C0 is not equal to 0 and C1 is equal to 0, we just go through this sum of our assumed form and have C1 equal to 0. So here we get, for example, C0 is just C0. We assume it's not 0. C1 is 0. C2 is 1/2 C0. C3 is C0 over 6, and on and on. And this forms one of our linearly independent solutions. And now for the second one, we go through the opposite, right? And again, we're still assuming that same form. Okay? We're still assuming that same form. And now C0 is 0. And we get, C1 is C1. C2 is 0. C3 is C1 over 6. Okay? And we get that proportional to C1. And then Y is equal to C0 Y1 plus C1 Y2, where now we found them. Okay, this is Y2. And this here is Y1. And we don't have a pretty formula for this, so we're just going to leave it as, a dot, dot, dot there. Okay? So this is just convenient. If you don't like it, you could just continue on with this and combine C1s and C0s just as we've done in the previous problems. But if you choose to go this route, remember that you're getting the same sort of expansion. Okay, you're turning off one versus the other, and so you have to use the same expansion. Which the only confusion here is that you might see, well, C1 is something here, it's 0, right? But C1 is not here, and then you get like C3, these turn out to be the same, but C4, this is C0 over 24. C4 here is C1 over 12. Okay, so just be cognizant of what you're doing, that you're turning off one of the solutions versus the other, and that you have to go now with both solutions and do each of these, okay? And technically we could have done that for previous problems, but it's pointless because here we want to get rid of one of them in the recurrence relation, okay?